Select the major product of the following reaction. So we see we are starting with an aldehyde. And we have hydroxide, so we have a base in this solution. And then we're adding to that slowly a ketone. So what this is this is an example of a crossed aldol reaction. So a crossed aldol means that rather than the self-aldol, where you have two equivalents of the same aldehyde or ketone reacting together, you're going to be using a different aldehyde and a different ketone. So in a crossed aldol reaction, you need to design your starting materials or your reaction conditions really carefully in order to get only one product. So this particular sort of crossed aldol reaction has a name. This is known as a Claisen-Schmidt reaction. And so what this is like we said, a very carefully designed aldol reaction. So you want to very carefully control what component acts as the electrophile and what component acts as the nucleophile. So we've got in a Claisen-Schmidt is an aldehyde that can only serve the role as the electrophile. And that's because this particular aldehyde, and there's other examples like it, has no alpha hydrogens. So it cannot form an enolate. So that means you are restricting the role of this aldehyde, that it is definitely going to be the electrophile in this reaction. It's not possible for it to form a nucleophile, okay? And so a Claisen-Schmidt involves an aldehyde with no alpha hydrogens, so that controls what your electrophile is, and then a ketone with only one type of alpha hydrogen. Because ketones, of course, you've got a carbon on either side of the carbonyl. So if both of those carbons had hydrogens, you'd have to start to think about things like kinetic and thermodynamic enolates. So if you have only one type of alpha hydrogen, then you don't have to worry about that. So you would see that if your ketone was symmetrical. Or in this case, you have a ketone that one side has no alpha hydrogens, the other side is the only side with the alpha hydrogens. So this is what's going to be converted into your enolate. So this is going to become your enolate. So that means it is going to be the nucleophile in the reaction. And so it is possible to do a self-aldol reaction with a ketone. So that's why we're doing things in the order that we are, okay? So you've got your solution of aldehyde with the base, and as you slowly add in this ketone, you're going to convert a small amount of this to the enolate, and then that enolate can react with the aldehyde. Aldehyde carbonyls, we should remember, are also more reactive towards nucleophilic addition than ketones. So that also helps to control this reaction. So what's going to happen is your base is going to convert some of this ketone to the enolate. And so I'm just going to jump ahead and just draw the enolate. We've seen this deprotonation quite a few times now. So if you remove one of those hydrogens, you will get this enolate. You'll convert a small amount of it to the enolate, but as soon as it forms, it should react pretty readily with that aldehyde. So here is the aldehyde. And so we will see this enolate attack your nucleophile, attack your electrophilic carbon. I'm going to push these electrons up. Standard nucleophilic attack on a carbonyl. And then we will see that we have formed a new bond between this carbon and this one. So here is the benzene ring, your carbonyl, and then you have that CH2 group. And here is your new bond that you formed to this carbonyl carbon. And so we broke the pi bond, so this now has a negative charge on the oxygen. And then we have the torpedo group that was attached to that. Okay, and so if you're doing this first step with base, and your base is hydroxide, it's pretty safe to assume that is in the solvent of water. So you've got some water around, most likely, at least a small amount. So we can protonate that. And so you would initially get this aldol addition product. And then we're going to be heating this up with aqueous acid. So when we do this, this is going to promote the condensation. So we've got our aqueous acid. We can protonate this oxygen. Okay. Let me slide this down so you can see it. So we've protonated that oxygen. And we're running out of some space here. So I'm going to take this down here. So slide this up so we can see. And so let me redraw what we had. So we had the benzene. We have the carbonyl. We now have this alcohol protonated. And so we're set up to do this kind of elimination reaction, right? So there we have it. And so then in the next step, what we can see is that we're going to eliminate water here to form an alkene. And so this is going to give us our aldol condensation product. So that would be the alpha beta unsaturated carbonyl. And this should unsaturate pretty readily because you're getting this extended conjugation from the benzene ring through the carbonyl to that alkene. So we're going to see, there's the product. You've also formed a little bit of water. All right, so that's the water that you've eliminated. So when you have a condensation, it's bringing together two molecules and eliminating a small molecule. And so hopefully you can recognize that this is the option A.